Okay, so everything should be working then. All right, so welcome back everybody to this N3AS seminar. We are very happy to have Jérôme Margueron joining us from Lyon. He's going to be telling us about the properties of neutron star crusts. And so Jérôme, whenever you're ready, we're very happy to hear your seminar.
Okay, thank you very much, Jeffrey, and thank you very much for the invitation to give this presentation online. Let me just reduce. Okay, so the purpose of this presentation is to present some recent work that we have done on the properties of neutron star crust, and our interest was to focus on quantifying and correlating uncertainties, together with put some improved nuclear physics in the description of the crust. And this is work that I've been doing with some collaborators, Sanjay Reddy from INT Seattle, and two young PhD student, Rahul Somasundaram, and postdoc Guillaume Grams. So it's clear that the work is mainly done by them. So let me start with some kind of motivations. So why? Yes, okay. So about neutron star observations, so we have recently entered into the age of accurate measurement of neutron star size extensions. By size extension, I mean radii or tidal deformabilities or moment of inertia. So this is really this is really a new feature which have emerged over the last years, thanks to new observations and new detections. So one of them is the detection of gravitational waves from the LIGO-Virgo Observatory. It had started in 2015 with the first detection of binary black holes during the O1 run. And then in 2017, it was the first detection of a binary neutron star during O2. And the latest observing run, O3, detected several things, and among the new feature, there was a binary black hole neutron star system which have been observed. And thanks to these new observations, we expect to know better gravity and cosmology, as well as dark matter and dark energy. And the present work is mainly focused on what we could learn from these observations about dense matter in neutron stars. Then, in addition to that, there is a nicer X-ray observatory from the NASA agency, which is this very small detector here that you can see on this picture, and which have been attached to the international to the ISS space station. Yeah. So this is a very nice figure, mass over the radius, which have been published by these people, Tan, Dor, Dexheimer, and others recently, where they summarize the present uncertainties about observations. And it's very interesting because they put together the LIGO-Virgo detection about 1708-17, which is shown here in yellowish or orangish, together with the two nicer detections of G0030, which is there, and G0740, which is here, which is one of the heaviest known neutron star, for which X-ray pulsations have been recorded and used in order to extract constraint on the mass and the radius. So as you see, I mean, these data are really new, I mean, 10 years ago, we had almost no ideas about about the possibility to have such precise determination of the radius. Of course, we expect that these techniques will even reduce down their uncertainty. There is also a bit before some analysis made of on the thermal emission from QLMXB. So these are quiescent low mass X-ray binaries using telescopes like XMM Neutron or Chandra, coupled with, for instance, measurements, distant measurements made by Gaia telescopes. And this this third way to determine the radius of neutron star is based on the fact that a few well-selected neutron stars have an emission spectrum very close to a black body. And therefore, one could hope to extract an information about the radius or an information about the compactness of this system. So as you see, since 2002 and especially after 2010, there were a lot of papers analyzing these results. And I will just briefly present a Bayesian analysis made by Nicolas Bayot-Detivo in 2019, which were based on 7 sources in a globular cluster, and where the equation of state were directly injected into the data analysis, while before the data analysis and the equation of state calibration were done in 2 different steps. And as you can see from these Bayesian contours showing mass function of radius, there is a preference for radii which are close to 12 to 13 kilometers. And together are put also the gravitational wave constraint in dash and the nicer constraint that was known at this time. So as you can see, there is a kind of consistency between all these results and all these different techniques which are used in order to extract very accurately the radius of neutron stars. Okay, so then that the motivation somehow have been presented, I'd like to briefly summarize what we know about neutron stars and why a better determination or better understanding of the crust could help us in order to go along this precision measurement. So neutron stars, they have mass ranging from 1.2 to maybe 2 or 2.2 solar mass, maybe a bit higher, but not so much. And radii, which presently are maybe between 10 and 14 kilometers. And they are made of different layers. The most external one is the atmosphere. Then comes the outer crust, which is composed of nuclear clusters and free electrons. Then comes the inner crust, where in addition, there is a neutron gas surrounding the clusters. And when the clusters get very close together, then they merge and we enter into the outer core, made of nuclear matter, uniformly distributed. And in addition to the neutron, proton, electron, muons are expected to appear at around the saturation density. And then we enter into the core of a neutron star, where the composition is presently totally unknown. And one of the main scientific aims of our work, the people working on neutron stars, is to have a better understanding of the composition of the core. So, and this composition is somehow correlated with an information about mass and radii of neutron stars. So the mass, we could know it pretty well, especially in binary systems, but the radii are really the new feature. Since we are now entering into observations that are able to reduce the uncertainty on the radius, on the side of the modelers, there is also a requirement that uncertainties on the radius, and especially the ones that come from the crust, should also be well under control. So this is the reason of the present work. So let me say briefly, and it's not totally exhaustive, so there's a lot of missing work there, but how the description of the neutron star have been done since the seminal work of Baim, Petik, Bethe, and Petik, the BBP equation of state back in 1971, where they employed compressible liquid drop model inspired by a compressible liquid drop by Myers and others that have been used for the description of the neutron star crust, where they implement the Coulomb and the surface terms. Then in 1973, there is Negele and Vautrin who have performed the first microscopic R3 calculation for the inner crust. Then there are a lot of works which have been done, but maybe one of the most important or known at the present time is the Duchin-Ansel equation of state from 2001, which is one of the first unified model. So unified means that the crust and the core are described with the same interaction. In this case, it is a Skirm interaction, SLY5. And this interaction has the advantage that it is calibrated on the experimental nuclear masses, as well as it incorporates some fit to prediction, to variational prediction for neutron matter. More recently, in 2016, Morgan Fortin and others, they underlined the importance of unified model to get accurate neutron star radii. So somehow their claim is that if one wants to have an estimation of the radius less than half a kilometer or less than a few hundred meters, it is very important to control the fact that the model for the crust is unified with the model for the core, at least for the outer core. And a recent work by Suleiman confirms this statement. A bit before, in 2008, Andrew Steiner, he have studied the effect of symmetry energy, compressibility, and the low density neutron matter effect on the composition of the crust. And then after Ingo Chu, in 2017, he introduced the recently proposed constraint from Karal EFT in neutron matter to calibrate or to reduce the uncertainty on the equation of state. And he found that still uncertainty in the crust are mostly coming from the neutron matter equation of state. And in parallel, there are several groups who have worked on the microscopic calculation and implementing the pairing contribution in R3 Bogolubov calculation. And for instance, a recent work that I will quote after is the one by Pearson in 2018, based on several BSK forces. So in this presentation, I will show some analysis of the crust properties where we have confronted two classes of equation of state. So they are all derived in the compressible liquid dot model, and one of these equation of state is based on the Carral-EFT predictions in symmetric matter and neutron matter, and the other is based on Skirm force, which had the advantage that they are calibrated over the nuclear charge, so they can give information coming from experimental knowledge. Okay, so let's start with uniform matter calculation. So I show here a comparison, the confrontation of these 15 equational states. So we have taken something like 8 equational states based on Carral-EFT. So these are these models in dashed lines. So H1 to H7, and then the DHS with 2 different values for the slope of the symmetry energy, L, 59 and 69. This equation of state have been derived by Duchler in different papers, 2016 and 2021. We confront this equation of state with 7 Skirm interactions that are listed here and that are represented in solid line. So the left panel is the usual representation where you see the energy as a function of the density, and the right is a bit less conventional because we have normalized the energy by the free Fermi gas energy, neutron matter, and on the x-axis, in order to zoom in to the low density case, we decided to represent the density axis in terms of the Fermi momentum instead of the density. So the Fermi momentum for saturated matter is about 1.33 inverse Fermi, so it is there. So you can see that the range that we explore are really the range inside the crust. So what we can observe here is that there is a very small dispersion in neutron matter based on the Carral-EFT predictions, while the Skirm suggests a very wide dispersion. So somehow the Skirm, though there is a big source of uncertainty on Skirm interactions in neutron matter, which is not present or is with a much reduced uncertainty when we employ Carral-EFT. However, now if we plot symmetric matter, you can see that the situation is inversed. So the Carral-EFT that you see here, for instance, hardly reproduce saturation matter. Even, I mean, it's not bad, but it's not as good as the Skirm ones. So the band from the Carral-EFT are much wider than the band from the Skirm, which are fitted to finite nuclei and therefore reproduce very accurately the saturation properties. Okay, so let's continue now. So the symmetry energy, so this is the difference between the energy in neutron matter and the energy in symmetric matter. It can also be obtained as an expansion in the symmetry parameter, where the first term is obtained as a second derivative of the energy with respect to the asymmetry parameter of delta. You can see on the left that there are different kinds of predictions, especially at high density. You can see on the inset that some of the Skirm interactions predict a bending down of the symmetry energy at a rather high density, but this has an effect on the softening of this equation of state, as we'll see later on in the core. On the right side, we play the same game as before. So we normalize the symmetry energy by the free Fermi gas symmetry energy, and we change the density by the Fermi momentum. What you can see here that again, the chiral EFT predictions are inside a pretty narrow band compared to the predictions based on SCRM, which are represented by the solid lines. And this uncertainty or this large dispersion is originates from the uncertainty that these SCRM interactions have in neutron matter. It is also interesting to compare that prediction with some experiments. So there are here the constraint by Daniel Levitz and Lee on the isobaric analog state in blue, and in dark blue putting in addition the skin constraints. And a recent observation by PREX2 team have pointed toward very large symmetry energy as well as slope of the symmetry energy that we represent here in yellow. And it is pretty in tension with all the models that we have investigated so far. So it is interesting to know that. And even the stiffest equation of state that we have considered, which are this DHS chiral EFT, are not as stiff as what PREX2 expect to have measured. So this is something interesting. I don't have much comment about it in the rest of the presentation, but this is interesting to know that there are some tensions with some observations, some measurements. Okay, I see that time is going on, so I will go a little bit faster now. So we just represent the pressure, and here is the constraint from GW 170817, and you can see that our equation of state explore entirely the uncertainty coming from that constraint. So that's not bad. Just briefly saying what we are doing for the inhomogeneous matter. So we describe the clusters inside Wigner-Seitz cells, so which represented there. You see the cluster in the middle, and around you have only electrons. So let me just say a few things before. So we have 4 variables, so 3 to describe the cluster properties, the mass, the charge, and the density, and 1 which describes the electron density, which is modeled as being uniform in the crust. If you write, for instance, the volume fraction occupied by the nuclei, so it's given by the baryon density over the cluster density. And since the cluster density is, compatible or close to the saturation density, so the volume fraction increases as the density increases. So when we go to the interior, to the inner crust, so this is defined as the point above which the first neutrons in nuclei drip out, and now we have therefore to deal with the presence of neutrons in the gas, which adds an additional variable to the description. And the volume fraction is now given by this expression. And since gas is very low, so the gas density is very low, the gas is very shallow, we can approximate the denominator by the cluster density, which again is constant. So you can see that the volume fraction still increases as a function of NB, but now minus NJ, and we'll see later that at the entrance of the inner crust, the volume fraction does not grow as fast as it was growing in the outer crust. And then we enter into the core, where the nuclei they merge together. Okay, and in terms of the adiabatic index, we can also rather well understand these different phases where the outer crust is, you can see the dominance of the electrons. Then you see this big softening of the adiabatic index induced by the neutron gas. And finally, the core, entering into the core, you see that there is a big increase due to the incompressibility of nuclear matter. Okay, so so time is going fast, so I will continue to go fast also. So one of the important feature in this compressible liquid block model is the possibility to order the different contribution to the energy according, for instance, to the leptodermal expansion. And this is one of the studies that we have done where we have analyzed the contribution of the different ordering as we go higher and higher in this expansion. So what we expect, of course, is that as we go higher in the expansion, if it is a good expansion, the terms contribute less and less. And this is what occurs, in fact. Another thing is that for the Chiral-EFT-based model, we can also confront them to the nuclear experimental masses, and we have used it in order to rank the Chiral-EFT Hamiltonians, as you can see here. So you have the loss function delta E, so the accuracy with which the Chiral-EFT could reproduce the entire mass table for the different Hamiltonians that you can see on the axis. And then you realize that, for instance, the Hamiltonian H2 and H3 are among the best ones. H1 and H4 are not bad, but then H5 and H7 are getting worse. So because of that, we decided to, in the rest of the presentation and the papers, to identify H1 to H4 as a good Hamiltonians confirmed by the confrontation to finite nuclei. Okay, then we describe the crust. So there are just a set of equations that I will skip, and I will show you the results. So here I show the energy at beta equilibrium. So the vertical band here represents the frontier between the outer crust and the inner crust. It's not a solid line because there are different models. So depending on the models, the line is different. So it defines a band here. Then the pressure at beta equilibrium in the crust, the sound speed at beta equilibrium, and the volume fraction. And here, as I was saying before, in the outer crust, you see that the volume fraction is increasing with NB, and as we enter into the inner crust, and it is still increasing, but with a lower rate, which is because of the contribution of the gas density in the previous equation. What can also be said from this figure is, for instance, at high density, there is a large uncertainty due to the Skyrm force. So that reveals the effect of the neutron matter. And indeed, we are in the upper edge of the inner crust. So the neutron matter is expected to play a big role. And in the outer crust here, we see that there are large uncertainties, this time due to the Chiral-EFT. And this is a region where the nuclei, the nuclear masses are expected to play a big role. And you can see that the uncertainty originating from Skyrm interaction is very small. However, the one from Chiral-EFT are pretty large. If we consider all of them, but if we select only to the one that reproduce well the nuclear charge, then there is a very good overlap with the Chiral-EFT and the Skyrm interaction. So in a way, this figure summarize one of the main results, which is that there are two important features which controls the equation state in the crust. One is originating from the nuclear chart or from the experimental determination of the binding energy that we know from accelerator physics, and the other, which is what we yet don't know about neutron matter equational state, and which become pretty large as we go deeper and deeper in the crust. Okay, so this is about the ordering, the convergence of the leptodermos expansion. So very briefly, you can see that the different colors, so from red to magenta, green, and black, you can see that we are going higher and higher in the ordering. And you can see that the differences for these different quantities that are represented here are less and less marked as one go from one to another. So this is an interesting feature as well. Okay, so just to finish, I'm more or less on time. We made a comparison of our predictions. So our best models are the CRL-EFT, which have been selected against the nuclear data. So these are represented by this gray band. Okay, so these are the H1 to H4 that we confront. So this is the mass and the charge of the cluster that we confront against previous calculation. Some of them are, pretty old. This is a BBP that I was mentioning before, or the Duchin-Ansel, or the Negelet-Vautrin, and some of them are pretty recent. These are the BSK calculations. So what we see that in the outer crust there is a pretty small dispersion because of the control originating from the nuclear masses, and in the inner crust there is a larger dispersion, which reveals the yet uncertainty originating from the neutron matter contribution. Okay, so maybe I will skip that and come to my conclusions. So in this presentation, I've discussed several features in the crust of neutron stars. One is the leptodermos expansion, and we obtain a result that this is a good expansion to order the different terms contributing to the crust properties. And the other is by confronting CRL-EFT Hamiltonians against current forces, we were able to underline the role of symmetric matter, or in another way, the nuclear mass determination of the experimental nuclear masses, and the neutron matter. And we were able to, to make a separation between different properties. One like the mass, the charge, the asymmetry, which are mostly determined by symmetric matter properties close to saturation, and therefore mainly constrained by experimental nuclear masses, and others like energy per particle, pressure, sound speed, electron fraction, which are mostly influenced by the neutron matter predictions, where there's a substantial difference between CRL-EFT and current forces. All these equations that I have presented, 15 in total, are available now on the Compose repository under the name GMSR. And this work is entering into, is a project, is a part of a project which aims at helping the simulations in astrophysics by providing unified equation of state. And for that, we are now working on extensions at finite temperature. So with that, I would like to thank you for your attention, and I'm available for any question. Thank you very much.
Okay, thank you, Jérôme, for that very interesting talk. I hope you all join me in a digital round of applause, as it were. So do we have questions then? Okay, let's see if there are any raised hands. It looks like not. Okay. It looks like Susan Gardner has a question. Susan, please go ahead.
Thank you very much for the nice talk. I just wanted to, maybe if you could set the disagreement between the chiral effective theory studies and the Sturm forces in context. Usually we understand in the context of chiral effective theory that there's an estimate of what we think the uncertainty should be. And so when we look at the differences, and they look very different, I wonder when we consider the nominal estimate of untreated next to leading order or next to the sub-leading corrections with the chiral effective theory, whether that softens some of the difference between, you saw, between SCRM and chiral effective field theory treatments.
Okay, yeah, so the breakdown of the chiral EFT and how this is impacted by the ordering in the chiral EFT approaches is indeed a very important feature and very new feature that that is brought by chiral EFT. In our case, we haven't investigated the role of the different orders in chiral EFT on the prediction for the crust, since we have targeted only the latest chiral EFT models at N2LO or N3LO, depending whether we speak about NN or three-body forces. So your question, I think, is whether there is, I mean, this can help in the understanding of the convergence in the prediction for the crust. So I think this is, yeah, this study is possible. We haven't done it.
Just add that. Thank you very much.
Yeah. Okay. Thank you.
Okay, and we also have a question from Tianqi.
Hello, Jérôme. That's a very nice talk. I have a question about your treatment towards the compressible liquid drop model. How did you treat the surface tension?
Okay, so I haven't I didn't enter too much into the technical aspect of the compressible liquid drop model. So let me find just yes, here. Okay, so yeah, or maybe before. Excuse me. Okay, so you are wondering about the surface tension, how this is determined. This is correct?
Yes, the surface tension will determine, for example, your nuclear size, the V and A will all determined by this surface tension, but you didn't talk about this parameter and uncertainty in the surface tension.
Yeah. So there is, yeah, there are somehow, so the surface tension is parameterized by three parameters. So the one is surface, is a parameter that reveals the strength of the surface tension in symmetric matter. And there are two additional parameters which reveal how the surface tension changes with the isospin asymmetry. So these parameters are controlled by the fit to the nuclear chart. except one which influences surface tension only for very large isospin asymmetry that doesn't exist on Earth, I mean, in finite nuclei.
Okay, thank you. And also one small question, all the SCRM interaction here is constrained by the binding energy only?
No, the different SCRMs that we considered there, for instance, are, I mean, there is an history behind each of these parameterization, and they aren't constrained only on the base of the nuclear chart. Some of them incorporate some additional constraints on top of that, but at least what we can say that they all reproduce finite nuclei.
Mm-hmm. Okay, thank you.
Okay, and it looks like the next question is from Sanjay.
Hello, Jérôme. Thanks for that nice summary talk. I have a question about, maybe you can comment on shell effects and its role in determining the clusters, the Z of the clusters. You know, the earlier calculations would have to choose between various magic numbers, right? It would just choose Z of 40 or Z of 50. What do you think the role of that is going to be in determining the composition of the cold catalyzed crust?
Yeah, thank you, Sanjay. Thank you for your question. Yeah, I think I mean, shell effects somehow are on the to-do list for the next iteration of this work. But if we consider shell effects within the leptodermos expansion, we should not expect to have a dominant effect. I mean, somehow the shell effect should not be larger than contribution coming from the bulk or other dominant effects. What I mean is that if the symmetry energy, for instance, forbids some value of Z, they will hardly be restored thanks to shell effects, which act on the side or on the margin of other bulk properties. So I mean, so it doesn't mean that it should not be included and treated, but it means that if it is included, it might not change a lot the present predictions. So one of the reasons I could say that is in this comparison, there are at least 3 calculations which included this shell effect. So these are the Nagel-Vautrin, the black triangle pointing to the down, and as well as the purple, the BSK22 and the BSK25. So if you look at these different predictions, except the BSK25, which is very stiff, so which has a symmetry energy that is very large, the Z which are predicted by these models are compatible with our band. So it means that we could expect that, I mean, the difference between our band and these predictions give an idea of how large are the shell effects. So do I answer your question, or?
Yeah, I think in part it does, but I wonder whether the shell effects are, how sensitive are the shell effects to the symmetry energy? I think of it as separate physical effects, you know, somewhat correlated but not fully correlated. And so if you, for example, you know, if you look at the predictions in the lower panel for Z from different chiral Hamiltonians, it seems that Z of 50 is kind of outside its reach at the onset of the shell effects, right? So if you see, say, around 10 to the -4, between 10 to the -4 and 10 to the -3, you can see that there is clearly a difference between some of these predictions.
Yep. So yeah, I'm not saying that shell effects aren't important. I'm just saying that they should be treated, but so for instance, if you have a symmetry energy that will bring your Z, so if you have, for instance, a very large symmetry energy, so you expect that it is pretty difficult to produce neutron matter because it costs a lot of energy, and therefore that will contribute to raise up the charge of the nuclei because you will get closer to symmetric matter. And this is, for instance, what is observed for the BSK 25. So the fact that these predictions are off our band is, to my opinion, mostly given by the fact that they have a different symmetry energy more than because they incorporate shell effects. But you see that shell effects, as you said, I mean, stabilize a lot the predictions, and therefore Z equal 50, for instance, in this case, are the magic number preferred by this model. So by putting shell effect, there will be less fluctuations in Z than without shell effects.
Okay, thanks.
Okay, and it looks like we have a question from Sophia.
Hi, Jérôme. Sorry, this is not actually a question. I just wonder if you have time to briefly describe the last slides you skipped about neutron star properties.
So this one?
Yeah.
Okay, so yeah, so this is going a little bit, I mean, beyond the scope of the study, which addressed the crust properties. However, we were interested to push all these models in the core and to explore what kind of mass radius relation this 15 equation of state we have produced would provide. So most of them, for instance, pass the criterion, I mean, reach 2 solar mass as an upper limit, but some of them do not. So this is a bit unfortunate. But the 3 models which were really very soft and doesn't pass this limit are also the models for which the symmetry energy bends down, and therefore the fact that the 3 models are these ones. So they are RATP, BSK 16, and SG2. And the reason so why they are so soft is because the symmetry energy is bending down. So there is an interesting correlation between the behavior of the symmetry energy at high density and the softening or stiffening of the equation state.
So I wonder you use some standard extrapolation in the EOS to higher densities, right?
Yep.
And I mean, these mass radius, they look pretty smooth and probably smaller symmetry energy in a standard way correlates to also softer pressure in high densities. Which parameterization or method exactly do you use here to construct the whole band of the EOS?
So the model that is behind and that we used, that we have calibrated on the predictions is called the meta model. So this is a density functional approach. So for the scale models, it reproduces exactly the same features. For the chiral EFT, of course, it reproduces up to the breakdown of the approach, and we were obliged to have a prescription at high density. So in a sense, it is an extrapolation of the chiral EFT that you see in dashed line.
Yeah.
I mean, we are pretty free to decide how to extrapolate these models because there is no guidance by chiral EFT. So we decided to take the same high order empirical parameters for all these chiral EFT models. So it's fixed somehow, just to illustrate the arbitrariness in this prediction. And we fix them so that they reach the 2 solar mass. So in a sense, if these models predict masses above 2 solar mass, it is by construction.
Okay, I see. Thank you for your answer.
Okay, do we have any more questions here? Okay, if not, then let's take a moment again to thank Jérôme. Again, we'll throw up a little clap of hands here. I will stop the recording, and then if people want to stick around for a bit and continue to chit chat, then that sounds perfectly fine to me. So let me just stop the recording here.